Hi there, this is Jacob Nash, and this is going to be lesson two on continuing looking at velocity and acceleration, as well as the units that we're going to use and significant figures. So let's first review the difference between average speed and average velocity. In the everyday world, these two terms are often interchanged. This is really not correct. And here's the difference between speed and velocity. Speed is what's called a scalar. A scalar is something that's just going to have one value attached to it. And so speed, all that we can know for speed is basically a unit of distance per times. I apologize, that's written wrong. It's not time per distance. Distance per time. So we can say the speed is 60 miles per hour. The speed is 15 kilometers per second or whatever. I don't know. That's random. But that's what it's a scalar because we don't know what direction it's going. That's all we know. So that's why we consider it a scalar. But on the other hand, velocity is a vector. And as we talked about in the last video with that picture of the Despicable Me, you might remember that a vector has direction and magnitude. So it has two things. So we have more information with a vector than a scalar. And so velocity, not only can we have a magnitude, so we know how fast or slow it's going, we also know what direction it's going from velocity. And this is the reason why velocity is what we care about, because in physics, direction definitely matters. That's going to make a difference of something, if something will be negative or positive, depending on what is perceived as being the positive direction. And it's important to note that we use displacement um, for average velocity, but just distance for speed. And those are not the same either, um, because once again, displacement is going to be a vector because it cares about direction. So going back to that idea of if I start somewhere on a circular track in a park and I run around it, when I get back to where I started, well, my displacement is zero because I haven't gone anywhere. But the distance is not going to be zero that I've ran. So that's the difference. So are speed and velocity ever the same? They can be. They are not the same thing, but they can be equivalent. Um, that just matters of because remember, velocity takes into account direction. So if we're in the positive direction, then the speed and velocity could definitely be the same. We're going to talk about now a couple common misconceptions that are important to know. So, constant velocity. Um, if we're talking about a constant velocity, that means a velocity that's not going to change. It's going to keep staying at a certain value. And you might think that that means zero acceleration. Well, graphically, that might make sense because we know that the slope of a velocity versus time graph is going to be the acceleration. And if we have a constant velocity, it's going to be a horizontal line. And the slope of a horizontal line is zero. So you might assume that means that a constant velocity always means zero acceleration. Well, graphically, that's oftentimes true. But we can have other forms of motion. For example, we can have a constant velocity going in a straight line, and yes, there will be zero acceleration. But if we're going around in a circle, like taking a curve in a car, even if we're at constant velocity, there is an acceleration there. So be careful about that. Another common misconception is a lot of times people will think that a positive acceleration means we're speeding up, and a negative acceleration means we're slowing down. But that is only sometimes true. What really will tell us if we're speeding up or slowing down is how velocity and acceleration are related. If they are doing the same thing, meaning both are positive or both are negative, then we're speeding up. But if they're doing different things, then we are slowing down. All right, now we're going to talk about the units that we're going to use. So it's very important to use the correct units for physics. We are going to use the metric units. That's more general or common. So the three that you'll want to know. If we're talking about length of something, we're going to use meters. If we're talking about time, we'll use seconds. If we're talking about mass, we're going to use kilograms. Now, there's definitely other units that we're going to see, but these are the main three. Um, Whenever you're solving a problem, make sure you never forget your units because if you do, then your answer technically is meaningless because if your answer is 12, uh, what does that tell us? 12 what? Because 12 inches and 12 meters are a lot different. So you got to be careful about that. Now, how do you convert units? So you may be familiar with how to do this already, which is completely fine. But in case you have always struggled with this, there's a very easy way to do it. Um, so you just start out with whatever you're starting out with. So let's say we had 38 inches and we want to convert this to feet. Um, Maybe we want to convert this to feet and then to meters. Sometimes you do that. You have multiple conversions. Just take it one step at a time if you need. But what you're going to want to do is multiply by the conversion rate. And what is that? Well, you may be given some of them, but in this case, you probably know that 12 inches equals 1 foot. So you multiply by that fraction, but you have to think the two numbers I have there are 1 and 12 because 1 foot equals 12 inches. So do I multiply by 1 over 12 or 12 over 1? It's always going to be to where the units cancel out. So you can see that since this is really 38 over 1 times 1 over 12, the inches cancel out and we're just left with the unit of feet. And that makes sense because we are getting a smaller number, and that makes sense for the conversion rate because 1 is smaller than 12, so our answer should also be smaller than 38. If we multiplied by 12, that wouldn't make sense. How could 38 inches be a bigger number in feet? That wouldn't make sense. So just make sure you do it the right way. Oh, sorry, I skipped a slide. All right, now let's talk about significant figures. So basically, in science, we have what's called significant figures, and they are telling us um, from our measurement what is significant to us. Um, Zeros are sometimes meaningful or sometimes meaningless. Never put a zero just for the sake of doing it. So if you measure something and you're only capable of measuring to the tenth, so it was 1.7 inches or something. Well, you're not going to put 1.70 because what that would indicate is that we have more precision to the hundredths that we could put that zero there. So even though 1.7 and 1.70 are technically equivalent, they mean different things in this class for us because one of them indicates that we had higher precision enough to add an extra zero or an extra significant figure. Um, if you're ever doing any mathematical operation where you're multiplying two units that have differing numbers of significant figures, because here we have 3, 4, 4, 5, and here we have 2, 2 and 7. What you're going to do is whatever your answer is, report in the same as the smaller number. So this had 3, this had 2. So our answer needs to have 2. Trailing zeros. So I was talking about how that zeros past the decimal point matter and are significant. But zeros like this are not considered significant figures. So this would have two significant figures and this would have one. And that's because it's called a trailing zero. That means that it's a zero, but it's not after a decimal point. So once again, these are not significant figures. They're not considered significant figures. That's because if you were to convert these to scientific notation, the zeros are going to be omitted. So I know that might seem a little bit confusing, but um, if you convert 160 to scientific notation, you'd have 1.6 times 10 to the 2. You're not going to say 1.60 times 10 to the 2 because we don't add that extra zero unless it means a more precise measurement, but that wouldn't be the case there. So alternatively, this one is considered a significant figure because it's after the decimal point. All right, let's look at a few practice problems based on what we just talked about. All right, this actually isn't what we talked about today, but in the last lesson, so it's still good to know. So let's draw a displacement vector from the yellow to the purple. It's just going to look like that. That's actually just as simple as it is. We're starting at the yellow, going to the purple. We just start the arrow at the yellow and end it at the purple. That's really just how simple it is if you get a question like this. Now, looking at this, what is the acceleration vector? Well, this is a little bit funky because, like, we don't actually see numbers here, so it seems a little bit weird. But remember, we can add or subtract vectors, and we looked at that in the last video, so review that if you don't remember, but you're going to see how to do it here. What is acceleration in relation to velocity? Well, it's going to be the change in velocity over time. Time, we aren't told, technically, but change in velocity is going to be v2 minus v1, because we're starting out with this velocity and ending at this one. This is has a higher magnitude. They're both in the same direction, but v2 has a higher magnitude. So that means that we need to subtract those because if acceleration is change in velocity over time, we need to find the change in velocity, which is going to be this vector minus this one. So what you do when you're subtracting vectors is you instead just still add them, but you just add the negative. So these two things mean the same thing. We just changed it to where we're adding by a negative. And the reason why we do that, if you don't remember, is because the steps that we use are applicable for addition, not subtraction. So that's why we want this to be here. So what we're going to do is we start out with the V2 and we want to we want to add the negative V1. Well, that means you just flip that backwards. So this V1, it goes here and you put it's tip to tail method. So you have the tip of this one with matching up with the tail of this one. Now, that blue, which is what's left, is going to be the answer for this. This is the V2 minus V1. Now you divide that by time, and that's going to tell us our acceleration vector. But obviously, in this case, you wouldn't get an actual number, but you have to visually be able to do it with the vectors sometimes. All right. So this sentence says acceleration is positive. Is the object speeding up or slowing down? We actually cannot answer this question. We cannot know just by acceleration if an object is speeding up or slowing down. Remember, we have to know what the velocity is doing. Also, if the velocity is also positive, then yes, we are speeding up. But if the velocity is negative, then these two things are contradicting each other, which would mean that it's actually slowing down. All right, looking at this graph, where is the object stationary? So what kind of graph is this? If you look at it, it's displacement versus time because I see x here and t there. Well, stationary, and for these units, is going to be where there is no change in the displacement. So that means we're not going higher or lower on this axis. So this is going to be a place where it's stationary. Also this, and these moments that kind of look like mountain cliffs and valleys are going to be places where temporarily it's stationary, but it's just because it's changing direction. So here we're just doing nothing. Then we're going back this way. Oh, stop. We're going that way again. Oh, now we're going down that way. And you might think that this means where it's stationary. No, that just means that is the position of zero. So that means that doesn't mean it's not moving. It just means it's at that specific place that is considered zero. All right. Next, we're going to say which one of these has the most significant figures. I didn't specifically discuss in super a lot of detail about what is considered a significant figure. So I'm going to do it here since I haven't. So let's look at A. Well, the zeros are not that are back here are not considered significant figures. These are, though, the 521. So that has three. This one has four because basically, as a rule of thumb, the ones that are not zero always are significant figures. The zeros are sometimes or sometimes not. If they are before the non-zero numbers, they are not significant figures. If they're after the non-zero numbers, they sometimes are. Only if it's after a decimal. So since this is after a decimal, yes, that zero is a significant figure. Down here for C though, that zero is not. That's called a trailing zero, as I said. So this one has three. So that's going to be it for this video. Thank you for watching.